From the transistor to the web browser. Hiring is hard. A lot of modern CS education is really bad, and it's hard to find people who understand the modern computer stack from first principles. Now, cleaned up and going to be software only, closer to being real. Section 1, Intro. Cheating our way past the transistor, 0.5 weeks. So about those transistors, course overview. Describe how FPGAs are buildable using transistors, and that ICs are just collections of transistors in a nice, reliable package. Understand the LUTs and stuff. Talk briefly about the theory of transistors, but all projects must build on each other, so we can't build one. Emulation. Building on real hardware limits the reach of this course. Using something like Verilator will allow anyone with a computer to play. Section 2. Bring up. What language is hardware coded in? 0.5 weeks. Blinking and LED. Verilog 10. Your first little program. Getting the simulator working. Learning Verilog. Building a UART Verilog 100. An intro chapter to Verilog. Copy a real UART. Introducing the concept of MMIO, though the serial port may be semi-hosting. Serial test echo program and LED control. Section 3. Processor. What is a processor anyway? 3 weeks. Coding an assembler, Python 500. Straightforward and boring, write in Python. Happens in parallel with the CPU building. Teaches you ARM assembly. Initially outputs just binary files, but changed when you write a linker. Building a ARM 7 CPU Verilog. Break this into subchapters. A simple pipeline to start, decode, fetch, execute. How much RAM do we have? We need at least 1 megabytes. DDR would be hard, I think, maybe an SRAM. Simulatable and synthesizable. Coding a bootdrum assembler 40. This allows code download into RAM over the serial port and is baked into the FPGA image. Cute test programs run on this. Section 4. Compiler, a high-level language, 3 weeks. Building a C compiler, Haskell 2000. A bit more interesting, cover the basics of compiler design. Write in Haskell. Write a parser. Break this into subchapters. Outputs ARM assembly. Building a linker, Python 300. If you are clever, this should take a day. Output ELF files, used for testing with QEMU, semi-hosting, libc plus malloc C500. The gateway to more complicated programs. libc is only half here, things like memscpy and memset and printf, but no syscall wrappers. Building an Ethernet controller, Verilog 200. Talk to a real PHY, consider carefully MMIO design. Writing a bootloader, write Ethernet program to boot kernel over UDP. First thing written in C, maybe don't re-download over serial each time and embed in FPGA image. Section 5, Operating System. Software we take for granted, 3 weeks, building an MMU Verilog 1000 ARM 9-ish, explain TLBs and other fun things. Maybe also a memory controller depending on how the FPGA is, then add the init code to your bootloader. Building an operating system, C, 2500, Unix-ish, only user space threads, open, read, write, close, fork, exec, v, wait, sleep, exit, mmap, munmap, and protect. Consider the debug interface you are using, ranging from printf to perhaps a GDB remote stub into kernel. Breaking into subchapters, talking to an SD card Verilog 150, the last hardware you have to do, and a driver FAT C300, a real file system. I think FAT is the simplest. Init, shell, download, cat, ls, rm, C250. Your first user space programs. Section 6, Browser, coming online, 1 week. Building a TCP stack 100, probably coded in the kernel. Integrate the Ethernet driver into the kernel. Add support for networking syscalls to the kernel. Send, receive, bind, connect. Telnet D, the power of being multiprocess C50. Written in C, user can connect multiple times with Telnet. Really just a bind shell. Space-saving dynamic linking, 300. Because we can, explain how a dynamic linker is just a user space program. Changes to linker required. So about that web C500+, a nice text-based web